made sure.
Okay, questions on the homework? This is 8.4. It's a series, I assume?
It's a series log of -1 parentheses to the power of n plus 1 over n plus 6 power. That's infinity and n equals 1, like in the figure.
Okay, what's the question?
So the series is convergent. So what term of the series do we need to add in order to find the sum to indicate its accuracy? And the error here is 0.40
And 5?
Yeah.
Okay, so if I call this a n, then notice that the series of absolute value a n is just a series of 1 over n to the 6, which is a convergent p-series. This means an not only converges, but it converges absolutely. Okay, that's that. But it's an alternating series, so we can use the alternating series estimation theorem. Since we know that the error is less than or equal to a n plus first term, we want a n plus 1 to be less than or equal to that guy. 1, 2, 3, 4, 5. So we have 1 over n plus 1 to the 6th is less than or equal to 1, 2, 3, 4, 5. So n plus 1 to the 6 is greater than or equal to, this guy's 5 over 1. So this will be what, 20,000? Yeah, so n must be greater than or equal to 20,000. Take the 6th root of that, and then subtract 1, the closest integer to this. Choose n equals the smallest integer greater than this number. What is that number roughly? I don't know.
4.21.
This is just 4.21?
Yeah.
So n equals 5 is, yeah, so n equals 5. So to get an approximation this good, I just need 5 terms of that series.
Do you need to do all that work? Can you just know that n is 5? Because like by a certain amount, like a big enough number, you know you will get that accuracy.
Yeah, you could have brute force it. You realize that your an is 1 over n to the 6th. So you realize, obviously a1 is 1, that's not going to work. What is 2 to the 6th? That's still not good enough because I need to get 0.005. So you can sort of maybe a to the 4th, 1 over 4 to the 6th. Is that big enough? You check that in your calculator. If not, you go to the next term, 1 over 5 to the 6th, and you realize that that one actually beats it.
No, what I meant was like, you see how it has 5 digits? Oh, that's 6. I know.
I don't remember how many did. 4 zeros and a 5.
Why
Yep.
did you make it less than or equal?
Because if it was exact, it was just good.
It doesn't matter either case.
No, it's just
Yeah, it doesn't matter. It says that can be, that's the most it can be, so we just write less than or equal to. The less than or equal to case sort of deals with the case where you have series where from one point onwards you have all zeros. So technically, after a certain point, it's equal to. It's a special case. It just covers all our bases. But yeah, that's basically it. So that was absolutely convergent. Just use the P series with the absolute convergence test. And then for alternating series, that holds. Any other questions?
35.
What does that say?
It's the series from 1 to infinity of parentheses 1 plus 1 over n
1 plus 1 over n.
plus parentheses to the n squared. And it was cannot say if it converges or diverges. Converges absolutely or diverges.
Oh, okay.
So I did the root test, but that only gets rid of 1 out.
I think it's gonna be the root.
Yeah, I do the root test. Notice that here, I have 1 plus 1 over n to the n to the n. Right? Now this guy I know. And the limit goes to infinity. So by the root test, I look at the limit as n goes to infinity of the nth root of that guy in absolute values. 1 plus 1 over n to the n to the n. This equals that. And so this actually gives me what's the limit as n goes to infinity of 1 plus 1 over n to the n. It's e, which is actually bigger than 1. So this diverges. Other questions?
Do we just have to know that?
Yeah, this is something you should know, yes.
It was again like one of those converge diverge axes. And it's the sum of 2n minus 1
Sum of 2n minus 1
over 2n minus 1 factorial.
over 2n minus 1
Oh, and times negative 1 to the n plus 1.
like that's in front.
There was addition.
Yeah, like that. And 1 to infinity.
37.
Is that it?
37.
There was
But wasn't it like 1 over e? Isn't it like 1 over e? Not e. So
1 over e. Where?
that. For the answer.
Oh, okay.
No, that's e. There was another one where there was 1 over e. Maybe you're mixing it up.
I think that's
That was
probably
actually like all the symptoms. I think I might have messed up the.
Oh,
the top
okay.
term, the top.
Yeah, like I wrote my own name.
Yeah, it's here.
Oh, they gave me like the thing is like 1 minus 1 times 3 over 3 factorial plus 1 times 3 times 5 over 5 factorial minus. Right, but it was fine to actually say that. This is just the series from minus 1 to the n plus 1. 1 times 3 times 5 all the way up to 2n minus 1 over 2n minus 1 factorial. Okay, so that's a series. Determine whether it's absolutely convergent, conditionally convergent, or divergent. Ideas?
To the ratio test. Ratio.
What test?
Ratio.
Ratio test would be a nice one to use. The root test, I wouldn't want to take a radical of all this, but I see factorials in there, so the ratio test is probably the best bet here. So I'd probably try that. So just take this here to be my an and do the ratio test. So I'm going to look at the limit as n goes to infinity of an plus 1, 1 times 3 times 5 times 2n plus 1 over 2n plus 1 factorial times the reciprocal of that, 2n minus 1 factorial over 1 times 3 times all the way up to 2n minus 1. Now a bunch of things are going to cancel here.
135.
2n and not 2n minus 4.
No. It's 2n plus 1.
It's 2n plus 1 minus 1. Right? Which is 2n plus 2 minus 1, which is just 2n plus 1. Right? The n's are replaced with n plus 1. Remember, you don't just put a plus 1 beside it. So that's what we're going to have. And what's going to happen?
135.
So this is going to cancel some terms here. It's going to cancel into this. I'm going to be left over with 2n plus 1 times 2n. That's that. Now all of this is going to cancel with a bunch of those. And so on top I'm going to have 1 times, I'm going to write it over here. I'm going to have 2n plus 1. The next odd power down is 2. That's all I'm going to do. That's just 1 over 2n because this cancels. That limit is 0, which is less than 1. So this is absolutely convergent. This we can take a couple more. Yeah.
Could you explain how when you canceled out the 2n minus 1 factorial and the other one you got 2n plus 1 times 2n?
Right, so I know that 2n plus 1 factorial, if I write that out, that's just 2n plus 1, and I keep counting down the integers. So that's times 2n, 2n minus 1, 2n minus 2, 2n minus 3, and that continues all the way down to 1. Right? Well, up to this point here is just 2n minus 1 factorial. Right? So then that top one is going to cancel all of this, and I'm going to be left over with this. This is what happened here. And similarly, this one is 1 times 3 times 5 times all the way up to, it'll be 2n minus 1 times 2n plus 1. So then all of this would cancel all of that. Because this one skips by 2. Right? So I add 2 to this, I get that one. So I know that the term right before this is actually that term. Other questions?
Can we do on 43?
Or it's in part A, that sounds serious. What is? One over n cubed? So you're just going to do the ratio test and see if you get a 1 as the limit.
Yeah, and I got to like the third step, which I got the limit of n to the infinity equals 1 over parentheses 1 plus 1 over n parentheses to the cube power.
Well, we look at this limit. An plus 1 over an. Right, that's 1, inconclusive. Ratio of polynomials, highest power on the top and bottom is the same, goes to the ratio of coefficients. So there's a 1n cubed divided by a 1n cubed.
See, I turned the denominator into 1 plus 1 over n, and then I said we could use it opposite 1.
So it was actually inconclusive for part A. Which is amazing. It's sophisticated, but that's a pretty easy series. We know that actually converges absolutely. But the ratio test wouldn't give us any conclusion with that. Anyway, let's move on. Is it 8.5? So I've been thinking, right? I know, crazy. What's the easiest kind of function to do calculus with? It's a trick question. If you had to do calculus on some function, what function would you want it to be?
Polynomial.
Polynomials. They're the nicest guys, right? You just have the power rule. You integrate them easily, you differentiate them easily. I mean, the only thing remotely as nice as the exponential, you know, derivative of e to the x, e to the x, but that guy can give you problems when you're integrating. Go e to the x squared and then we're dead, right? Polynomials, they're really nice to integrate and differentiate. They're really nice to do calculus with, so follow me here, but I was thinking, right? Is there a way to like write any function as a polynomial? You know what I mean, man? You know, like, yeah, last night I was there, man. Right? Is there a way to write any function as a polynomial? Well, if there is, I want to know, right? But so let's think of some of the challenges here. Look at a function like sine x. What's an obvious challenge with something like sine x?
Alternate.
Like, how do polynomials behave at, say, their ends? They go to positive or negative infinity, right? So if I give a random polynomial, the endpoints are either going to shoot down to negative infinity or going to shoot up to positive infinity. Well, with a function like sine, that's obviously a problem because sine bounces between plus or minus 1. So we know when polynomials actually do this. You can actually predict it in some fashion, right? The degree of the polynomial tells you how many turns it can make before shooting off to infinity, right? So an x squared can only make 1 turn before shooting off to infinity. X cubed can make at most 2 turns before shooting off to infinity, so on and so forth. If you know the degree, 1 less than that degree will determine how many, the maximum amount of turns you can have before it shoots off to infinity, right? So a function like sine is also a nice function. It's continuous everywhere. It's basically easy to do calculus with that. And I would want to be able to represent this as a polynomial, but then there's the obvious hiccup, right? It doesn't shoot off to infinity. How would I prevent that, you think? So I know, so if I have a polynomial, right? You know that after a couple turns, it shoots off to infinity, and this is bounded by the degree. What if we made a polynomial of infinite degree? Right? It'll never have to shoot off to infinity because I will never go 1 less turn than the highest power, right? So with something like an infinite polynomial, I could probably model a sine. I don't know if it's even possible, but it would be really cool if I could do it. Or any other crazy function. It would be really cool if I could turn it into a polynomial, because calculus with polynomials is extremely nice, right? So let's actually explore this idea that I'm making up on the spot right now. I'm just thinking, you know. of something I'm going to call a power series. I'm coining that phrase. And basically what I'm going to do is I'm going to try to develop the idea of an infinite polynomial. So I'm going to make a definition. A power series is a series of the form. What does a polynomial look like? There's some coefficients, right? Let's call it C. And then there are x terms that are raised to powers. So let's actually write it like that in case I want to represent some sort of center. It's like the equation of a circle or something. Right? So I define that to be a certain kind of series, which I'm going to call a power series. Basically, if I write this guy out, what he looks like is C0 plus C1 x minus x naught plus C2 x minus x naught squared plus C3 x minus x naught to the fourth, and so on and so forth. I'm just increasing a polynomial. My x naught is a constant, which I'm going to call the center of the power series. Just like how it'll be the coordinates of the center of a circle, similar to that. i.e., I can call this guy Cn x minus x naught to the n. N goes from 0 to infinity. The power series centered at x naught. Okay. So I created this thing. I don't even know if it makes sense anymore, but let's imagine that we could do this. Make a polynomial of infinite degree. How would I sort of control something like that? How would I know how that would behave? Like, where would that converge if it actually converges to anything, for example?
Second, you take the original first derivative, there's no values that you convert to.
I don't know about derivatives, but not yet anyway. I'm not that sophisticated yet. I'm just trying to think about this. What kind of convergence test would I use here? Maybe a ratio test. It's a pretty complicated thing. I don't know what these numbers are in general. Let's figure out its convergence properties. Let's do a ratio test on this guy. See what we come up with. If I call this guy my an, and I look at the limit as n goes to infinity, Cn plus 1 x minus x naught to the n plus 1 over Cn x minus x naught to n. What's going to happen here? Well, this guy's going to cancel with that guy. And I'm basically going to end up with this guy here is just a constant, right? Let's call that a constant. So this basically is going to give me L is equal to some constant times x minus x naught. Exactly. Right? So now to converge, what do we need for this to converge? It has to be less than 1. We need x minus x naught times a to be less than 1, which means I need my x minus x naught less than 1 over a. Let me call this something else, something more suggestive. Call this constant r. right? The distance between an x value and the center point I can think of as a radius of some sort, right? So I call this r for the radius, and I'm going to call this guy here the radius of convergence, right? That's how far away from this thing I can move before I can't converge anymore.
We change C, right?
Well, the limit of Cn plus 1 over Cn, right? These two are just constants,
Yeah, so.
right? So if I divide them, I get a constant. The limit of a constant is just a constant. I just call that constant A, whatever.
Okay,
So it turns out that this guy I can call the radius of convergence. It's literally giving me an interval of x values where this convergence will actually happen. Right? It's called the radius of convergence. However, we remember our absolute values. I can expand this guy like this. And then I could write something like x naught minus r is less than x less than r plus x naught. Now this is actually an interval. Let me call that the interval of convergence. I'm not sure what goes on at the endpoints. It might converge, it might not, because when my limit is equal to 1, it's inconclusive. So it might converge at the endpoints. I'm not sure. That's sort of something I'll test on a case-by-case basis. Because the ratio test doesn't tell me anything about that. Okay, so if such a thing could exist as a series, this will have to be some property you'd have. I would know where it converges based on that kind of theorem. My x minus x naught must be less than or equal to a constant in absolute values. That constant is my radius. And this will give me my interval where this series will actually make sense. It will actually converge and give me a number, which is really important. So it does make sense at some level. Right? So let's actually write this down a bit more formally. What are the cases here? There are three cases. One, right, I'm talking about the power series Cn x minus x naught to the n from 0 to infinity. One, I can say it converges. By the way, it converges absolutely, which is pretty important. Right? It means it won't change if I rearrange the terms. It converges, right? On the interval x minus x naught less than r. So that's one thing that can happen. What's a second case? It converges only for x equals x naught. That's also a possibility, right? Because if I plug in my x value equals x naught, I just get 0. I'm adding a bunch of zeros. It's going to add up to 0. So it could converge if my x equals x naught. Could converge on some interval. A third case is, as you'd have clearly seen in your homework, it's possible to get the ratio test and you converge for everything. If I take this limit, like when you were doing your limits in your homework and you got something like 0, for example, right? 0 is always less than 1, regardless of what your x value was, regardless of what your n value was. That means like it works for anything. Right? Your x wouldn't matter in that case. It's interval of convergence is the whole real line. Those are three very basic consequences. This one I had to derive a little bit using the ratio test. These two are sort of from common sense from practicing our problems in 8.4, right? So if I'm adding zeros, I'll converge to 0. Or it's possible that this limit is completely 0, in which case my x values don't matter. I will converge for any x value, right? So those are three cases for my power series. This thing that I didn't really make it up. I think just don't want anyone to go, oh, my professor invented power series. I don't know, some of you guys can be gullible. I trick you out, guys, about we're having a quiz all the time. I just want to make sure. Didn't really invent it. Okay. Yep. That's basically it. So essentially, I will make one more note before moving on. Since the ratio test is inconclusive, this is an important. If the limit of an plus 1 over an is equal to 1, meaning you're right at the endpoint, endpoints must be tested for convergence. So there are several possible intervals of convergence, right? So for example, one interval could be x minus x naught is strictly between r and minus r, or it could be less than or equal to minus r, strictly less than r. It could be less than this guy, but strictly less than or equal to that guy. It could work at both endpoints, or either one, right? We don't know the endpoints, we have to check. There are 4 possibilities here. So it can not work at either endpoint. It can work at the lower one, but not the upper one, or work at the upper one, but not the lower one, or it can work in both. It's something you'd have to check. You'd have to check each endpoint, which I guess we'll get to that later. You'll see me write this when I get lazy. IOC, interval of convergence. ROC, radius of convergence. Let's look at some examples. Theory is great and all, but what does it all mean? It would not be strange for me to ask you, or for you to see on the final, what is the ROC and IOC of some series, right? It's possible for them to ask you to find the radius of convergence. So here's the examples. X to the nth power, n goes from 0 to infinity. I also want you to tell me, what does this converge to when you get there? Another example, what if I gave you this and goes from 1 to infinity of x minus 4 to the n over 2n c. X to the n factorial from 0 to infinity. So basically tell me the interval on where these converge. What x values, at what x values do these functions work? Let's look at part A. How to figure out where this will work?
You use tests like the determinant?
Like the what?
Like you use like different tests, like you use like the geometric series test list?
Well, I want to know what interval it works, so that's probably not going to help.
Well, yeah,
If you
because
tell me
you
the
know
answer.
with the geometric series that's between -1 and 1. Because of the rule.
Okay, yeah, that is a geometric series. So can you tell me what it converges to? So this is geometric. That's one way to do it. So converges, we know if x is strictly less than 1 in absolute values. And by the way, it diverges at the endpoints. Right? Because if I plug in 1 for your x, your limit doesn't go to 0, so test for divergence shows that it diverges. So you could have done that. What does it converge to? No?
Does it convert to x?
What? 1 over 1 minus x. Right? Remember, it's a over 1 minus r. My r is obviously x. My a is the first term. When I plug in n equals 0, I get 1. So it's 1 over 1 minus x. This means something strange. The function 1 over 1 minus x, I can literally write it as a power series. I can write this guy as if he were a polynomial if my x is on a certain interval. Right? This guy is a polynomial. It's 1 plus x squared plus x cubed. If my x is within 1 in absolute values, this polynomial, this infinite polynomial, is actually equal to this function. We'll get back to that. Another way to do this, which I'm going to, a more conventional approach. If you didn't recognize that's a geometric, of course you're not going to get anything that easy on a test, but just a more conventional approach. So pretty much for these problems, you always use the ratio test. It's pretty much always the guy you use. And they're going to give you something where the ratio test is going to look nice. Pretty much always use the ratio test. So if I'm given x to the n and goes from 0 to infinity, I'm going to do by the ratio test. I'm going to look at the limit of an plus 1 over an as n goes to infinity. This cancels that. This literally gives me just absolute value of x. Set this less than 1 for convergence by the ratio test. Right? Basically, we force this to happen. Right? Right? So I set it less than 1 by force, and it turns out, what is that? That tells me exactly the interval of convergence that we knew from the geometric series. It coincides with the conclusion of the ratio test here. So this means my radius of convergence is 1. Now let's talk about the interval of convergence. For IOC, I need to test the endpoints. I know it works with the strict inequality, so let's test the endpoints. right? If x equals 1, what is my series? I have the series of 1 to the n. From 0 to infinity, this diverges by test for divergence. If my x equals minus 1, I get my series from 0 to infinity of minus 1 to the n. And again, diverges by test for divergence. Right? So I don't work at the endpoints. So this means my interval of convergence is the interval from minus 1 to 1, not including the endpoints. So that's my interval of convergence. This is my radius of convergence. So basically this series works, I'm not at minus 1 or I'm at 1, it'll work everywhere in here. Meaning within that interval, this power series actually converges to a function. In fact, I know what function it is because it's a geometric series. I can figure out what the answer looks like. That's not always, it's not always going to be so obvious what it converges to, but knowing it converges is good enough. So here, I've been able to express this particular function, 1 over 1 minus x, as an infinite polynomial. It's just that guy, and that works as long as my x is within a certain restriction. That is 1. What was the second one? I think it was x minus 4 to the n over 2n. Did I want to write 2n there, or did I want to write 2 to the n? I think 2 to the n would have been more interesting, but let's do 2n anyway. Any questions so far? Like if you're faced with one of these questions where they ask you for a radius of convergence or interval of convergence, this is sort of how you would attack it, right? Do the ratio test. You're going to get an interval, right? What are your x minus x naught will be in here, and whatever number is on the outside, that's your radius of convergence, and then you have to test the endpoints to figure out the interval. We're going to do it again with this one. So yeah, employ the ratio test again. So what do I have? I have the limit x minus 4 to n plus 1 over 2 n plus 1 times 2n over x minus 4 to the n. That goes into that. So this limit is equal to what? X minus 4 times 2n over 2n plus 2. If I take that limit, what do I get? As n goes to infinity. What's the limit of x minus 4 as n goes to infinity? Just x minus 4. It has no n's in it. What's the limit of 2n over 2n plus 2 as n goes to infinity? 1. So that's that. Set that less than 1 for convergence.
So do that last time again.
Well, this is just right here.
Yeah.
Yeah, so I have this limit. So I'm taking the limit. This has no n's in it, so that's just itself. This guy goes to 1, right? Ratio of the coefficients, because the highest powers are the same. So this just ends up here. Now I set this less than or equal to 1 for convergence, right? Because I know that's where the ratio test converges. Right? So I force it to be less than equal to less than 1. Right? Because that's what I need for convergence. If it's outside that range, it doesn't converge. So now, this means my ROC is again 1. Now let's look at for interval of convergence. Let's figure this guy out. Slightly more complicated than it was last time. Basically what I'm going to have is I have x minus 4 is less than 1, which means minus 1 is less than x minus 4, which means I can add 4 to both sides. This is 3 is less than x less than 5. Right? So my x range is between 3 and 5. Does it work at 3 and 5 though? Not sure. Let's test. So now let's test the endpoints. What if x equals 3? What does my series become? Well, I go over here and I plug in 3. Right? Now if I plug in 3, what happens? What do I get? I get minus 1 to the n over 2n. Does that converge or not?
Yes.
Yes. How do you know?
It's an alternating series.
Alternating series, so what's the test?
It's decreasing and either the that and also increasing.
Right. Converges by alternating series test. So it turns out I do work at 3. Okay, what about 5? My x equals 5, what does my series become now?
1 over 10.
Just 1 over 2n. Converge or diverge? Diverges. Right? Because it's harmonic. All right, I can factor out the 2 and I get the harmonic series. This means my interval of convergence is 3 inclusive all the way up to 5 not inclusive. Meaning that infinite polynomial over there converges to some function whenever I'm on this interval. Outside this interval, it makes nonsense. Yeah.
You feel like right that t is less than equal to x less than 5.
Yeah, it's the same. I'm just using interval notation. Here you can use inequality notation. That's perfectly fine. That's my interval of convergence. This infinite polynomial behaves very well on this interval. Like it converges to some function. What function? I don't know particularly with this one here, but I know it converges to something. We'll sort of figure out how to find those somethings later. But so far now I know it converges. Converges absolutely, so it's definitely some function that is not going to change if I rearrange terms or anything like that. Converges absolutely to some function on this interval. Right? So what was the third one? X to the n over n factorial. From 0 to infinity. Find the radius of convergence and interval of convergence. What do we do? Ratio test, always. Did any of you guys see Turbo? The snail movie? Yeah. It was like, left turn, what do I do? Oh no, left turn! He's like, it's always a left turn. He's like, he didn't understand why everyone was so fascinated by NASCAR. But yeah, like, whenever you see this, what do I do? It's always the ratio test. Like, it's always the ratio test. Right? Like, when you see a problem like this in a test, you don't freeze up. It's always the ratio test. Okay. Just do the ratio test. If I ask you for radius of convergence or interval of convergence, it's the ratio test. So let's look at that limit. X to the n plus 1 over n plus 1 factorial times n factorial over x to the n. This goes that. This goes that. So I'm pretty much left with x over n plus 1. And what is that limit?
0.
That's 0. Now, the funny thing about 0 he's less than 1, and he's less than 1 always. Right? Notice x does not matter. Right? Meaning any x can work.
Whatever x would be there.
So x could be whatever he wants to be. I don't care. It's going to be less than 1. So that means that guy actually works everywhere. So here, the radius of convergence is pretty much infinity. And the interval of convergence is -infinity to infinity. So radius of convergence here is infinite. It works on the whole real line. My x value does not matter. My interval of convergence also is the whole real line. Everything. Turns out that that series is actually a function that we know what it is, right? This guy is x to the n over n factorial. This is pretty much the polynomial 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 plus dot dot dot. It's actually a known function. We know exactly what it converges to. I'll leave you in suspense for a little bit. Does anyone know what it converges to? G to the x. That's actually your exponential written as an infinite polynomial. That would be hidden. It turns out that this is e to the x. How do you know that? Well, I'm glad you asked. I'm going to tell you right now. We're moving on to 8.6. Do I actually tell you at this point? No, I tell you about something else and then I tell you how we know that. But I'll tell you soon. I'm going to show you how to represent a bunch of odd. No. Odd actually means something. Weird functions as power series. The fact that these guys behave like polynomials, because they are polynomials, is we can use that to our advantage. We can differentiate them easily, we can integrate them easily, we can do this with the series as well. By the way, that's something to think about. You'll notice that if you differentiate this, you actually get itself back, right? Derivative of 0 is 0, derivative of x is 1, derivative of this is x, that is x squared over 2, that's x cubed over 6. You differentiate, you get itself back. It's literally, it is e to the x. This is e to the x. Right? So whatever we can do with the function itself, we can do it with the series, and it will behave just like the function. It is the function on whatever interval this thing converges to. So let's actually move on. We saw, this is one that we use very commonly, so it's actually something you should have memorized. That 1 over 1 minus x is the series x to the n from n goes from 0 to infinity for x is less than 1 in absolute values. Right? That's known now. That's just something you know now. Use this fact to determine the power series the following. So we're actually going to go through several of these guys. Here's an innocent looking function, 1 over 3 plus x. Right? I'd like to tell me a series that actually converges to that function. And also tell me where they converge. Should mention that. Where does your series converge. E. F of x is 1 over 3 plus x squared. C. F of x is ln of 3 plus x. Part A. Tell me a power series for that guy. Using this guy. Right. The idea is try to make this guy look exactly like that guy, and then we can translate, right? By composition. So this 1 over 3 plus x, what I could have done is I could factor out a third. I'd be left with 1 over 1 plus x over 3, right? Which almost sort of looks like that guy. The problem is there's a plus sign in the middle, and I want a minus sign in the middle. So I just write this as 1/3 times 1 over 1 minus a minus x over 3. Now notice that this minus x over 3 is sort of in the same position that the x is in the original. So this guy, I can literally now just throw in a series to represent him. So this is going to be 1 over 1 minus x is what? X to the n. So it's just going to be this guy to the n. This is going to be from 0 to infinity. So I have 1/3 times the series from 0 to infinity of minus 1 to the n, x to the n, over 3 to the n. Or if I like, I can bring this 3 back in and end up with this series. 0 to infinity, minus 1 to the n, x to the n, over 3 to the n plus 1. Where does this converge? Right, so just as how that converges when your x in absolute value was less than 1, this converges when our new x in absolute value is less than 1. So I just put minus 1 over 3 less than 1. This means x is less than 3 in absolute values. So it converges for minus 3 less than x less than 3.
And we don't know if that's the endpoints or no from this.
Yeah, we know from this that the endpoints don't work. If they don't work there, they're not going to work here. Because I'm using that guy to my advantage. Right? So it works on this interval. So my x can be as big as 3 or as small as minus 3. Once it's in that range, this series is that function. Whatever I can do to that function, I can do to this guy. But this guy is a polynomial. So whatever I need to do to that guy, it's a lot easier to do with this guy. Yeah. Because we proved that in the last section. 1 over 1 minus x converges to x to the n if your absolute value of x is less than 1. So I know that this holds. I know it doesn't work at equal to 1. Because I already proved in the previous section, it was a geometric series and all that, it didn't work at 1. So I just take the same idea here and express it. I know it's not going to work at the endpoints. And you can test it if you'd like. It's not going to be hard. The test for divergence will kill both your hopes. So yeah, I represent this function as a power series, and I know exactly when it works if my x values are between those. If my x value is outside that range, tough luck, can't do a series. Yeah. Oh, here the radius of convergence is the number, right? It's 3.
It's not like less than 3. It's not.
No, it's just 3. Right, the length of the interval 0, 3 and 0, 3 are exactly the same length. You throw in one more point on the real line, it doesn't change the length. Okay. Here's another one. What about this function? 1 over 3 plus x squared. How do I represent that as a power series? Anyone?
Take the square root of both sides and then do it.
You want to take the square root of an infinite polynomial?
Oh,
I wouldn't. Think calculus. What is this guy?
Can you expand it or do it twice?
Expanding wouldn't help.
Do it twice? Like 1 over 3 times
1 over 3x times 1 over 3x. So I write this as an infinite polynomial, that times an infinite polynomial. Let's multiply them together, multiply out. It's going to take forever.
Can you
Well,
do it
technically I
together?
could do that, but there's a far more efficient way. Think calculus.
Thank you.
Huh? It's not calculus. How does this guy relate to the guy I just did?
Can you square the whole thing?
You guys are thinking too hard. Calculus is going to go crazy. It's the derivative of this guy. Right? Right? If your y is equal to 1 over 3 plus x, this is equal to 3 plus x to the minus 1. I take y prime. I get minus 3 plus x to the minus 2. Right? So I get minus 1 over 3 plus x squared. Right? So this guy is the negative derivative of that guy. Right? Think calculus.
How does that help?
You take the
Tell me,
derivative of
what is
that.
this guy?
You take the derivative of that half.
This is the series minus 1 to the n, x to the n, over 3 to the n plus 1. Now that guy is a polynomial. How do you differentiate that? Right, bring the power down, subtract 1 from the power. That's right. All right, so this is minus 1 to the n, nx to the n minus 1. Right? Because this whole thing here is a constant with respect to x. I just differentiate the x term, nx to the n minus 1. This minus 1 I can bring in, multiply that minus 1. So I get minus 1 to the n plus 1, nx to the n minus 1 over 3n plus 1. That is the power series for this guy.
Jhevon? I'm not gonna lie, I don't know what you just said.
To go from here to here,
Yeah.
I differentiated.
And then after that.
Do you get the derivative? I just differentiated this term.
Okay.
Right? Because it's a polynomial. These are just going to be like c1 plus c2 x squared plus c3 x cubed plus going up.
How'd you get rid of
So I differentiate by bringing the power down and subtracting 1 from the power. That's going to happen for every x value. So I just do it with the power series. This is called term by term differentiation. So I differentiate this. This is just a constant times x to the n. The derivative is n x to the n minus 1 times the constant. Okay? There's a minus 1 on the outside, so I just multiply that in, because I can bring constant factors inside. So minus 1 times minus 1 to the n gives me minus 1 to the n plus 1. So that's a power series for that new function. If I realize that I know the power series of one function, I can find the power series of its derivative or its integral, because it's just like doing it for a polynomial. Right? And again, the interval of convergence will not change. This will still work for x3 and minus 3. So ROC and IOC do not change. For integrals or derivatives. Power series. Okay, let's do this one, part C. ln of 3 plus x.
Is it the same concept? Because the derivative of that is real.
This is, how do I write it in terms of 1 over 3 plus x? It's the integral of 1 over 3 plus x. Okay. I integrate that guy, I get this guy. So now I can integrate the sum from 0 to infinity minus 1 to the n, x to the n, over 3 to the n plus 1 dx equals. So basically what I did last time, I just switched the summation and the integral. I guess I should have made a note of that before, but how do I know I can actually do that? Is that kosher? Why can't I just swap the series and the integral?
Because the series makes it a polynomial. So that's a single polynomial.
Yeah, but basically what am I saying here? I'm saying the integral of the sum is the sum of the integrals. That's what I'm saying. How can I say that? How do I know that's true? That's obviously true in the finite case, but how do I know it's true? I'm going to infinity.
Last time you said like they behave same.
Isn't it because, like, you know, when you do an integral, you're taking the area of the different spaces and it's the sum of it?
I'm not sure. Over finite sums, yeah.
Because the sum is an n and the integral is in terms of x. So they don't.
Nope, that has nothing to do with it.
Yeah, it's
I'll give you a hint. If I had this guy, minus 1 to the n over n dx, I could not do this. X.
Is it the integral test?
That would actually be illegal in this case. Well, kind of. Depends on the x value. What we talked about last time, absolute convergence is the only reason we can do this. Right. Remember, your sum has to behave for you to do this. Right? There's a possibility that I could rearrange this term and get a completely different thing, get a completely different integral. The only way I know that nothing's going to be affected is because I know that this is absolutely convergent. How do I know that's absolutely convergent? I use the ratio test to figure it out. The ratio test gives me absolute convergence. So this sort of thing that we do here, this manipulation of switching the derivatives on the summation, or switching the integral of the summation, it can only work if you have an absolutely convergent series.
You have to capture that before you do something.
No, the nice news is power series are absolutely convergent whenever they're convergent. So if I know I'm developing it from a power series, I don't have to test it. Because remember, how did I figure out where the power series converged? I used the ratio test. And I forced it to work with the ratio test. Once the ratio test works, I get absolute convergence. So yeah, power series, wherever they converge, whatever interval they converge on, they absolutely converge on that interval. So I can switch integrals and derivatives and do calculus with the series just as I was doing with the original function. It only works because of absolute convergence. That's sort of why the idea is important. It allows us to do calculus on infinite sums. It's not something you can just assume will work in general, because it actually won't work in general. Right? But if our series is absolutely convergent, I can switch this, and now I just integrate term by term. So how do you integrate that? You get minus 1 to the n, x to the n plus 1 over n plus 1. Don't forget your calc 1, it's still important. That's it, that's my power series. Well, there's one more hiccup. You see a hiccup? There's a plus c. Don't forget the plus c. How do I figure out what that plus c is? Well, if I was doing a definite integral, I wouldn't care. But what if I want to leave it indefinite? So basically here I'm saying ln of 3 plus x is equal to this series minus 1 to the n of x to the n plus 1 over n plus 1, 3 to the n plus 1 plus c. This is to infinity. So here's a trick, just plug in an x value and solve for c. That's essentially how you do it. If I let x equal 0, what would I get? I get ln of 3 is equal to the sum of 0 plus c. This means my c is just ln 3. In other words, ln of 3 plus x is equal to the series
That honestly comes off as the most tedious thing to find. C. I also have to find C.
Yeah, if it's an indefinite integral, you should find c. But usually, you'll plug in whatever x value makes this 0. So you don't have to worry about the infinite sum being a factor. So I just plug in x equals 0, that kills this guy, and then plug it 0 on both sides, solve for c, and then I put the c back. So the power series for this guy is that. So you might be wondering why power series are, why do we even care? And we'll talk more about why we care next time, but for now, here's some motivation. I'm going to give you a little bit of motivation with the last example. So a few years from now, you're working on something insanely important and you come across this integral and you need to sort of find an answer for it. How would you do it? Forget series. How would you do this integral?
Break it up to instead of fractions, you can't now.
You can't do it, exactly. Tough luck, right? Not integral, right? Well, it wasn't integral before we learned about series, right? Saw this in Calc 2 or Calc 1, impossible problem, literally impossible. Well, let's sort of work around this. That's a nasty function to deal with, but calculus is nice with polynomials. Could I write that as a polynomial? Yes, I can. I can think of that as that, right? And what's that? Right? Basically, I can think of this as x times 1 over 1 minus x to the 9. So this is just x times what?
The series of negative x to the 1.
Minus x to the 9th to the n. Right? In other words, this is the series from 0 to infinity of minus 1 to the n, x to the 9n plus 1. And of course, this works for x less than 1 in absolute values. Outside that range, tough luck, right? Integral is impossible. As a Riemann sum, it will not converge if your x values get too big, right? However, if your x values are within 1 in absolute values, this guy behaves like that power series. And it's absolutely convergent on that interval, which means this is actually equal to what? I just integrate this guy. Right? So it's minus 1 to the n, x to the, add 1 to the power, 9n plus 2, divide by the new power, 9n plus 2. Of course, plus c. So now here's the idea. Because of course in the real world, you're working on some sort of project, you're not going to have an indefinite integral. You're going to get definite integrals. There's something that you need to figure out, you know, how much of something you need to use to fulfill some sort of requirement. So let's say you were given, or you needed to find out something like the integral from 0 to 1/2 of x over 1 plus x to the 9th, right? For some reason, right? The good thing about that is these x values between 0 and 1/2 fall within this interval. So that's good, right? It means I can actually do this. I can know that this integral is a series from 0 to infinity of minus 1 to the n x to the 9n plus 2 over 9n plus 2, where my x is evaluated between 0 and a half. So I can plug in x equals a half. I get minus 1 to the n over 2 to the 9n plus 2 times 9n plus 2. If I plug in x equals 0, I just get 0. So this integral on this interval is literally that series. What is that series? What does that converge to? I don't know. But could I get as close to the answer as I want? Sure, because it's an alternating series, right? So I can be like, I need to figure out this integral. I can't do it with regular calculus. Use a series. But oh no, I don't know what the hell that is. We don't need, our computer only goes up to 15 decimal places. We don't need to know exactly what it is. Just tell me what the answer is to 15 decimal places. It's an alternating series. Uses the alternating series approximation theorem. I can tell you exactly how many terms you need to compute to get this integral within an answer of 15 decimal places. Right? So this is sort of one of the uses of series. There are many, many, many uses. But one thing is, there are integrals that come up that you can't really deal with. You can't really integrate them using the laws of calculus that you learned in Calc 1 and 2. However, with series, now we can. And sometimes even if the series is a real mess, we often know how to approximate these series. We can get the answer to within any degree of accuracy we want to be useful. Right? So I can just do the alternating series estimation theorem on this, and I can figure out what that integral is. Right? Or as close to it as I want. So that's one use, and this is actually something you will have to do in a final at some point, so let it sink in for a while. We'll do more of it on Thursday.
So would they just simply tell you integrate that? Not even tell you, just say integrate?
They're usually nice. They will put this in a section where they tell you to use series to find the integral. But yeah, if you see something like that, you can't integrate it. There is no antiderivative, right? It's literally an infinite sum that it can diverge based on where you are. So it's really a nasty integral. It looks simple, but it's actually pretty nasty. However, empowered with series, it's actually not that bad. Throw this in your computer, tell it to compute the first however many terms you need, and you're done. We'll pick up more on Thursday where we talk about Taylor series. Basically, we're going to learn how to develop series for other random functions. Sort of do this.
Is it going to be a short test again?